story really started. In fact, very few people that know that the same guy, Kozlov, well, these, of course, knew, Kesten, Kozlov, and Spitzer, they found out when they came to Moscow. And as far as I know, this is how this famous paper has been written. That, if I am not wrong, it is Kesten who came and met Kozlov there. And this was, and they wrote their famous paper from 1975. And Solomon, as far as I know, was a student of Spitzer. They have a strange tradition there in Ithaca that they get students who write extremely famous papers and then disappear from this scene. On this list there are two of them. This is Solomon and Key. I hope I have him on the, yes, 85. So it's difficult to explain it without.
What do these papers do, Ilya? What are these papers talking about?
I will explain that. This is I'm talking to you as if you ever heard of them.
I know nothing about these.
But yeah, that may well happen. But it is very strange to anybody who has ever been involved into this business. But you haven't, so you are excused, of course. So what these papers do? What Solomon did is the following thing. He looked at the following random walk. With probability Pn, the particle can jump to the right or to the left. With probability 1 minus Pn. So this is 1 minus Pn, which will be Qs. Pn, in his paper, Pn was a sequence of IID random variables, independent, identically distributed. And he fixes this sequence, chooses a typical sequence, and the question is, what will happen with the random walk x of t omega 0, where 0 is the starting point. So if this is 0, then the random walk starts from here and then starts going back and forth. And the question is, in what case this random walk will be recurrent, in what case you will have some linear growth or sublinear growth or who knows what. Sublinear growth is something that has never been expected in anything like that.
Growth of moments.
No. Of the x of t is the coordinate of the walk. So I start at time 0 here and I look what is happening after time t. So after time t, the random walk is, this is the coordinate of the random walk. So it's the simplest model that you can have. Of course, a simpler one would be already when these Pn and Qn do not depend on n. But then it is, of course, the most classical thing which we explain to students. But if it is depending on n and say is IID in a non-trivial way, so that this Pn really is not a constant still, then the question is what will happen. And Solomon proved the following thing. So here, I may return to this list, but he was the first to prove the following theory. This is a theory. I hope you can see it well enough. Or is it too late? So he introduces the following quantity. Lambda is equal to the expectation of Q divided by P. You can split it. But it doesn't depend on J because I suppose they are identically distributed. And lambda larger than 0 implies.
In your slide is written expectation of logarithm operation.
Sorry, I should have written log here. This thing will also appear, but Yeah, this is exactly the thing that we need. So lambda larger than 0 x at t tends to minus infinity with probability 1. For almost every environment, if you fix the sequence of Pn, the random walk will run away to minus infinity. Lambda less than 0, of course, we have a plus infinity here. That's the only difference. And so this is in fact necessary and sufficient, and the necessary and sufficient condition. And lambda equals 0, x of t is recurrent. Recurrent means it returns to the origin infinitely many times. That's all what it means. And also one could say it crosses every point on the line infinitely many times as t tends to infinity with probability for almost. This is how the trajectory behaves. It goes back and forth and so on. What Solomon also discovered is the following thing, that if you have the expectation, well, let's introduce this function of q divided by p, no matter which one, q divided by p, without the log. If this is less than 1, and lambda is less than 1, then we have a linear growth. Then x of t divided by t converges to some parameter mu. But if expectation of t, so there are two conditions. Lambda is less than 0, that means that the random walk runs away to plus infinity. It is transient to the right. But whether it is transient with a linear speed or not depends on the other parameter, on this one. So if it is less than 1, then fine. If it is not less than 1, then this is wrong. Then, so if expectation of q divided by p is larger than 1 or equal to 1, then x of t divided by t tends to 0. So it's a sublinear growth. So this is the beginning of the story, and the paper is famous because of this discovery, actually, which is simple. If you look at how it is done, it is simple, but it was not expected, as far as I can understand. Okay. So what Kesten, Kozlov, and Spitzer did, they looked at this function in the case of IID random variables. Is it possible to read it, or should I write on the board?
What are your A's? Oh, the A's are, I see.
These are the A's. So let's introduce this function, R of alpha. Okay, I'm afraid I have to get rid of it. It is anyway the last sheet that I wanted to use, and I will simply write it on the blackboard. How do I get rid of the screen? Okay, thanks a lot. And what? I should simply...
Does anybody know, do we have today seminar after? Oh.
Okay. So R of alpha by definition is lim sup n tends to infinity of the expectation of the product aj to the power alpha j from 1 to n and all of z to the power 1 over n. Well, I wrote a formula which is useful also for the case when you have simply a stationary random environment, and this is what I will be talking about. I mean, I will be interested in this case. But if these guys are independent, remember that aj by definition is qj divided by pj. If they are independent, then this is a very simple thing. This is equal to, so if IID, then R of alpha is a very simple characteristic. It is an expectation of q divided by p to the power alpha. A very simple thing. There is one more interesting case when you can more or less explicitly say what is R of alpha. And this is the case when Pn is given by this, well, it is always given by, can be considered as P of t to the power n omega. T is some ergodic transformation on the space of environments. Omega is the space of environments, and, well, roughly speaking, T is simply the shift. But if omega is, say, a compact metric space, say an interval, 0, 1, and T is uniquely ergodic or uniformly ergodic.
Has to be uniquely ergodic for this?
Uniquely ergodic means there is only one invariant measure.
That's a requirement? That's a strong requirement.
It's a strong requirement. For instance, quasi-periodic. If omega is a number, so in this example, T omega is omega plus alpha, or let's say plus beta, where beta is irrational, modulo 1. Modulo 1. So, yes?
What is the statement? Because
I haven't yet made a statement. I'm only describing the sequences, the systems for which I can make the statement. And just explain. So if there is a uniformly ergodic system, that means that the ergodic theorem for sufficiently good functions works for all, not for almost all omega, but for all of them. So if P is a continuous function on 0, 1, this will happen here, where beta is, well, omega is, beta is irrational. Then I can introduce again the same Lyapunov exponent, lambda, expectation of the log of q divided by p. And then it is easy to show that R of alpha will be e to the power alpha times lambda. For these systems, you have also that. So there are two cases at least when this function is controlled in a natural way. It's easy, relatively easy to control. Of course, if we believe that we can find the integral here or here. It may be difficult. There are many difficult integrals on 0, 1. So I'm introducing this characteristic simply in order to explain that this function is actually more important than one could see it already here. Because this is a particular case. This is R of 1. But it is, in fact, more important than this one because, well, just the derivative of it over alpha at 0 will be the Lyapunov exponent. This is what the Lyapunov exponent is. So Keston, Kozlov, and Spitzer actually described very precisely what is happening with this random walk, in what case and what will be the limiting distribution of x of t properly normalized and how to do that. I will not go into that because we shall not.
Is it only in one-dimensional situation? Or
Not just in one-dimensional, but it is absolutely essential that it is one step to the right and one step to the left. The technique they used is, for the technique they used, this was crucial. And the task was, one of the tasks was to extend this thing to the case when you can jump several steps to the right and several steps to the left. It took some years to do that. And well, the list of people I showed you is a very small part of the list of people who worked on these problems. And recently we published with Bolthausen starting from our first paper was published in 2000, and then the 3 papers during the last year, which were
remind what it in this setting is Sinai case.
Yeah, I'm coming to that. So, in 1982, Sinai showed that if lambda is 0, so after Keston and Kozlov and Spitzer dealt with all cases except of this one in 75. In 1982, Sinai showed that there is a so-called Sinai diffusion, a very famous paper now, quoted very often. And he showed the following thing, that if lambda is 0, and the variance, say, of p is strictly positive, I simply want to say that p is a non-trivial. It doesn't have to be equal to 1/2. It has to take at least 2 different values, so that we really have the random environment and not just the classical random. So it's an empty statement. It's just that it is non-trivial. There is also a technical condition like all these p have to be less than 1 minus epsilon, larger than epsilon, which is larger than 0. Not really essential at the moment. Right? Then, so this is Sinai. X of t divided by log t squared converges in distribution, has a limit. A weak limit, a very weak limit in fact. Because it is not with probability 1, it is in the so-called annealed setting. We allow, in every experiment, roughly speaking, we choose a new environment and we look at the random walk after time t in a new environment. Then we do it again, again, again. Then this thing will have, this random variable will have the distribution, which is a limiting distribution. This distribution was computed by Keston and Golosov. Actually, Golosov and Keston. Independently, around the same time, 1986. And Golosov wrote a couple of very nice papers where he also described this behavior of this random walk in very precise terms. But so this was the situation for a while. It lasted like that, and actually in his paper, Sinai asked the question, what happens if we have not just this random walk, not just one step to the right and one step to the left, but what happens in a case when we have the possibility to jump several steps to the right and several steps to the left. And there were some papers written also about that before we started to look at it. I will not go now into history, otherwise I will never come to any new results. But anyway, this random walk is thus characterized by the sequence of vectors P and K. It is now natural to introduce these probabilities. P and K, this is n plus k. It is a probability of jump from n to n plus k, P and k, given that the random walk is at point n. If you know that it is at point n, it jumps to n plus k with this probability. So each point is characterized by this sequence k, say, from minus m to n, by the sequence of probabilities. Obviously, the sum of p and k is 1 over k minus m to m. And the question is, how do we deal with that? And as I said already, the problem with the technique which they used was that it was really somehow restricted to the case of the nearest neighbor jumps, because some equations there can be solved explicitly.
So in the Sinai case, do you assume that the environment is independent?
Yes.
That's necessary?
Independent of what?
No, that's
On point.
on point. The environment is chosen from a sufficiently good sequence. It's sufficiently well mixing sequence of random variables. It's not absolutely crucial, but it is actually very important.
Well,
there are some other cases. That's what I want to say. But Sinai considered the case of independent. Okay. So what I will consider is a slight extension of this model. I will look at the following random walk. I'll have a strips here, and this walk, or the particle, will be allowed to jump to one of these points.
Lambda will be 0. Lambda will be 0.
There is no lambda at the moment because it's not clear what is lambda. There are no two parameters, and it is one of the problems is to say what will be lambda actually, because there is no simple way to do it. No.
Probably that there is no bias.
Yeah, but what this is the meaning of, well, this number is the bias, right? Of course, in a sense, there is no bias. What will be this number which will tell you is there bias or not? This is the first question one has to ask in this model, right? So you have, I will explain the answer right now, but you will see that it is not immediately obvious what the answer should be. Not a priori. You cannot say it just looking at the problem.
Three lines, right?
Well, 3 or m does not
what
matter.
can be.
Any number of lines. I'm on a picture. I want simply to have 3. Okay. So m lines. Now, the rule is the following, that from each point you can jump to any of the neighboring points in this sense. Anything on the right, but not more than one step to the right. Anything on the left, the same thing, and inside. So in principle, that's what you need. Now this thing, so of course, again, each point is characterized by a huge number of probabilities. In fact, how many? 3n minus 1, or 3n actually. 3m probabilities. 3m probabilities for each point. Right? Because from this point I can return or to jump to other, and all the number of points. In each layer we have m points, and there are 3 layers. So I can jump from this point to any of these. And there are 3m of them, or I can return, stay in the
You
point.
can go up, you can go down.
I can go up, down, to the right, to the left. And there are 3m points in 3 layers, and that is it. Okay?
Here it is 9.
I want to divide these probabilities, which characterize just one layer, into 3 groups.
Just a simple question.
Yes.
You have in this picture m equals 3. Right?
Yes. So there are 9 points. 3 times
But
3 will be 9.
I count it's 3.
Sorry?
I count it's not 9.
3 times 3 will be 9.
No, this is correct, but central point you are sitting.
Staying
1, 2, 3, 1, 2, 3, 1, 2, 3. What is the problem?
also staying.
You can stay.
Yes, I said
You are
it.
not obliged to.
I said it.
Okay, okay.
You can return. You are allowed also to return to the point.
To remain.
Well,
To
whatever.
explain, it's
It's a
you
virtual
from.
step.
Okay, to remain.
Return.
To remain. No, but you know,
Clear.
this is how people say it. They usually look at this work and they say either this. And this means it stays.
Now it is clear.
Okay, fine. So, more importantly, I would like to divide the probabilities which characterize one layer. I would like to divide into 3 groups. Probabilities Pn, of course, this is the number of the layer along this line, of ij will be the probability jumping from ni to n plus 1 j. So I will write it in such a symbolic form. If I am here and and there is something to the right, and it will be n plus 1 something, j, say, then this probability I will denote Pnij. This will be a matrix, m times m matrix. Pn consists of these, Pnij. I can have probabilities of jumps to the left, Qn, I will say Qnij. So I do something a little bit less obvious than looking just at the probabilities of jumps. But it is still a very elementary. And then the probabilities to remain will be R and Ij. To remain inside the layer, you can jump from here, from N to N, to Ni to Nj, no problem. Okay, so the only restriction here, as you can easily figure out, is that Pn plus Qn plus Rn will be a stochastic matrix. That means it is very convenient to write it in this way. That means that the sum of the elements along a row of this matrix is 1. In other words, if I apply it to a vector which has all the components which are equal to 1, it will be 1. And actually, this is a very, very convenient analytic characterization simply of the property that the sum of the probabilities of jumps, of all jumps from each point is equal to 1. This is nothing else. It's a very simple thing. So, my random environment, so far there was no randomness. I just say, okay, you have 3 matrices, you have this.
This total are 1. What is that?
1 is, by definition, is this thing. 1, 1. Okay? So far, there is no randomness, but now I will take these Pn, Qn, Rn, independent, say, identically distributed. This will be the random environment. Now, I'll say 2 words about the reduction of this model to this one. In order to reduce this model to this one, all what I have to do is to divide the line into pieces of length m. If the largest jump, if it is from minus m to m, I will take m points, then next m points, and so on, and will turn these intervals by 90 degrees. And I will get a ladder. It doesn't matter where I start. Now, if you look carefully, what will happen is that from each point you will have this property, exactly this property. That from each point you can jump either to the right or to the left, no more than 1 step. In principle, you can jump to any point inside. In fact, not to all points here and here, but it doesn't matter. So this is a particular case of this model. So once you have a nice model, one of the very interesting models which are considered in this theory of random walks and random environment is this one. And I will not go to more examples. When you really jump only to the nearest neighbors. This is a very important and particular case of this model as far as the strip is concerned. And also, it is of course interesting to look at the case when the strip is growing and it is approximating the plane. That's another story, very far from being finished. Okay, so how do you go about that? What will be the analog of what I said before about, for instance, of this lambda? No simple way to define it, but there is a way, and it comes up when you do the analysis. You have to consider the following sequence of stochastic matrices. Psi n is one minus Rn minus Qn psi n minus 1 to the power minus 1 Pn. I do a very formal thing now. I write the following recurrence relation. Psi n is a sequence of stochastic matrices, non-negative. It is not immediately obvious that if psi n minus 1 is stochastic, then psi n will be stochastic, but it is very easy to verify. It's a very easy exercise. If you multiply, you have to check this equality. You simply substitute it, multiply by this thing to the power 1, and using the fact that this is stochastic and this equality, you immediately get what you need. So psi n, if I start with psi a, say this is a here, and go to the right, from psi a, any psi a, then I get psi a plus 1, so on, psi n. And then a tends to minus infinity. Then there is a limit. It turns out there is a canonical limit for this matrix.
What means canonical?
Well, canonical means the following, that it doesn't depend on the choice of the psi a. So it is defined only by the sequence. It is a function of the sequence. In this sense, it is canonical. Under very reasonable conditions. I will not go to technicalities.
But you didn't, or maybe you said, I missed it. What are assumptions on distributions of PNs, QNs?
Well, independent.
Just independent satisfying this, so they are not.
Well, that's one condition,
Totally
so they
independent.
can't be entirely independent.
Yeah.
One variable has to be.
No. The triples are independent. Otherwise, they are more or less arbitrary. You have 3 matrices every time. Of course, there is this condition there, right? But this is a huge vector. In what the dimension of this space is what? 3m squared minus m. Is the dimension of this space. Now in this space you have a distribution. This is a random thing. But then otherwise, but for different values of n, they are independent. I'm not saying that inside they are independent. They are of course dependent on each other. You have these relations. Yeah. Not, well, you can easily see that if you choose these probabilities which are independent of each other and somehow distributed in a reasonable way, you will always have it. You always have these things. So this is a very mild restriction. In fact, many things extend to the case
But
of.
it makes it one-dimensional because independence now comes about by moving forward, backward in a definite direction.
Yes,
One
yes,
layer back.
yes. Not in this there, not in the vertical
That's
dimension.
not a good assumption in order to study the limit of a growing width of the transverse direction.
No, it's a very good assumption if you can study it. The problem is not with this assumption.
2 or 3 dimensional.
No, it's, let's say, 2-dimensional. Then you will have these matrices of growing dimension, but they will still be independent. If you have the standard random environment where you can jump only to the nearest neighbors, this is exactly the model. This is exactly the model. You simply have a layer of large width, and you have a matrix of this size, matrices of this size, and they are independent. If these probabilities are chosen in an independent way, probabilities of jumps from each point are chosen, then everything is fine. There is absolutely, that is not the difficulty there. The difficulty is at a different place. Now, okay, let me try to. So, if you look at it carefully, this is in fact a Markov chain. This psi n is a Markov chain. And what I said, this limit, as in, will have the distribution, which is the invariant distribution of this Markov chain. Because it is clear that the distribution of this guy depends only on the value of this, not on anything that happened before that. So it's a Markov chain. Okay. I will introduce matrices AN, which are equal to 1 minus Rn minus Qn psi n minus 1 to the power minus 1. The only difference will be that there is a Qn instead of Pn there. Qn are the jumps to the left. And it turns out that lambda is the following number.
This is back to left, right?
Yeah, these are the matrices which will be responsible for the behavior, and what will be lambda? Lambda will be the Toplyapunov exponent of the product of these matrices. So, in other words, it will be the limit 1 over n log of the norm an a1 as n tends to infinity. This will be left. Now there is a complete analog of what I said before. Lambda is positive. The random walk will run away to the left, to minus infinity, negative to plus infinity, 0, it will be recurrent. But, as I said, this lambda is not immediately found just by looking at the system. You have to do something in order to understand it. And of course, you can easily check what is happening in dimension 1 in the classical case. In the classical case, Rn, well, first of all, the dimension of these matrices is 1. So these are simply numbers. P, Q, R are numbers. The ones we had before. R is 0. What is a 1 by 1 stochastic matrix? 1 by 1 stochastic matrix is also not a very difficult object. It is 1. Now if you substitute here a 1, you will see that this is P divided by P, and it will be again 1. So this equation is trivial. You simply don't see these objects there. They are not there. If you look at what is Z, it will be exactly the same A I wrote before. So this is a particular case. You will have this product. This will be a product of numbers. It will give exactly the same number as before. You can probably guess that I will introduce the function R of alpha in exactly the same way as here. Where is it? Upstairs. Yes? But what the difference will be that I will put a norm of the product in the right order from, say, n to 1. One has to follow the right order. I will put a norm here to the power alpha. And this will be exactly the analog of this function. And it turns out that this is what is responsible for the behavior. So
you never told us, at least I didn't hear what the function R of alpha is good for. So there's a characterization of the behavior in terms of R of alpha.
yes, I said that if okay, I really didn't. You're right. Well, I mentioned it, but very implicitly. I will say it now. I was going to do it anyway. If R of 1 is less than 1, this means psi of t, x of t divided by t converges to some mu which is positive. X of t is a coordinate, is a horizontal coordinate of the walk. It starts at 0, so for almost every realization you have this property. So it grows. I always, well,
That's assuming that R prime at 0 is also negative.
yeah, it's also positive, negative. Just one. Lambda is less than 0. I'm too much used to it, so that I forget to mention such things. Of course, you have a complete reversal situation when the reversal of the situation when lambda becomes positive. I don't know why. There's something with the light.
Still visible.
Visible. Okay.
Sorry?
Oh, okay. You're back.
This is exact.
Lambda is 0. Of course, means recurrence. I will deal with this case in a minute. I will mention only that if R of 2 is less than 1, a part of Z. So usually if then of course R of 1 is also less than 1, and I also suppose that, then there is a central limit theorem. Then this implies CLT. But this essentially is necessary and sufficient for a linear growth as it was before.
Central limit theorem in which sense?
Variance grows more slowly than.
You froze the environment, and there is a linear growth, but then you subtract something.
You ask what will be.
Yes.
You subtract the drift.
Yeah, what you subtract is actually a very non-trivial quantity. It is not deterministic. It is random. But I don't have the time to explain it, so I want to say several words about the case lambda is recurrent. Lambda is 0, and we have recurrence.
But Sinai case.
The Sinai case, yes. So what happens in the Sinai case? We will suppose that it will be essential that these triples, P and Q and Rn, are independent. If it is not like that, it may be different. Now, let us consider the following submanifold in the space of these parameters. We have this space of parameters. It is 3m squared minus m parameters. For every PQR, I can consider a vector pi such that pi p plus q plus r is equal to pi. Since this is a stochastic matrix, this is the invariant measure of a Markov chain on a space m by m. I'm going to define a subsurface in the space of parameters. So you need this. And so this vector is a function. Pi is a function of p, q, r for an algebraic function. Then I will consider a condition now. A set which I will call L, the set of triples P, Q, R, which satisfies the following condition. P times P minus Q times 1 is 0. I can write this in a very simple way. It is the same as to say the sum of P of ij minus Q of ij, sum over I and j is 0. This, of course, is not satisfied, whereas the pi exists for every triple. This, of course, is satisfied only on a subsurface. This is a non-trivial condition, algebraic condition. And in order to state the theorem, I need this subsurface in the space of parameters. And the theorem is the following one. This is Bolthausen and myself. That if the distribution of Pn, Qn, Rn is not supported by L, then given also that lambda is equal to 0. Psi t, sorry, x of t divided by log t squared has a non-trivial limit. Non-trivial limit. It may not look as a particularly simple condition, but this is more or less necessary and sufficient for it.
Non-trivial limit means equal to a number.
No. Means a distribution, non-trivial distribution.
In 1D, what was
Yeah, that's what I was going to say. Thanks. What happens in the original question, with the original question of Sinai in 1D, when you have jumps to the right, length m to the left. This condition, which that's what I was going to say, it doesn't look very simple at first glance, but it degenerates to the following condition: the sum of k, p of n k is 0, k from minus m to m, for all p of nk. All from the support of the distribution. You have a random sequence, it has to satisfy it. And this is the necessary and sufficient condition for having Sinai behavior in this case. Not just here, it is a sufficient condition. What happens when there is this equality can be more complicated. One has, in order to characterize this case, when you really have that many parameters, you have to work more. But in one-dimensional case, it gives a complete answer to the question. There is a complete answer to the question. You have a very simple condition. The meaning of that is very simple. This simply means this is the mean value of a jump from point n. If you always jump with a mean value of all jumps for all environments is 0, in this case you will not have the Sinai behavior. It will be the central limit behavior, by the way. It will be a diffusion. But if you don't have it at one point, and you know that the walk is recurrent, you will have the Sinai behavior. So this is a necessary and sufficient condition. And I think that's all what I have time for. That's 3.
Are there any results in high dimensions? I mean, just to know, because I don't know what is known about analog of Sinai diffusion.
No, there are no results, and strictly speaking, they are not really expected in high dimension.
Higher dimensions. There's Snitman and Kupiana and Brickbone.
Yes, there are many results about higher dimensions.
Which are analogous to this.
But they are not analogous to this. They are,
Why not?
because this is the central limit behavior always. All what we at the moment know, all the cases which were solved in higher dimensions, in all cases, which were considered in higher dimensions, and in higher dimensions, higher than 1. 2 is very high, and probably one of the most difficult. You have a left, and you have a random walk with which is allowed to jump to nearest neighbor, always. And this is one of the main ones. Now, if you have the full plane, there is a series of papers about the 3-dimensional case, starting from dimension 3. That's what is known. If you have a small perturbation of the classical random walk, small and somehow symmetric in the sense that there is no bias. You always have to say in this or that way that there is no bias. Then you have the central limit behavior. So you have the probabilities 1 over 6, but you perturb them slightly in a random way. And then you ask the question what will happen. And this is Brickman Kupiainen in 1980. And then there were some improvements. But still it is a difficult question. In dimension 2 it is Bischoff, I think, here from Schnittman, Schnittman, I said from Zaituni in the conference. That's what he's going to tell us, what is happening there. There are partial results there now. But there is nothing like senile behavior, and it is not expected. It is a one-dimensional phenomenon. And what could be done, I believe, is that if there is, say, if there is a line in the middle, and this may be a very interesting problem. And from here, the random walk is pushed into this direction, and from the top, from above the line, it is pushed to the line. So from all places it is pushed to the line, then there may be a chance that there is a senile behavior, at least for the projection.
That there is a bias which drives
Yes.
it towards the...
Yes, that's what I mean. The probabilities of jumping down are larger than the probabilities of jumping up, in the simplest version. Then you may expect something like that, at least for the projection of the coordinate of the walk, because the walk will be hell knows where. And in this direction, it certainly is not clear what it will be, but on the projection, you may expect something like log squared t.
That's it? Thanks.
Thank you.
Yeah.